Okay, so this week we're going to start well, we've been doing kind of cloud stuff, but we're not really taking full advantage of the cloud up until this point. I'm going to give you a broad overview of the cloud and how we got here and why it's important for you to learn it, and then we'll get into specific services in the cloud that I want you to explore. I'm going to start out at a meta level. This is a quote from a book that says, "The illiterate of the 21st century, this century, will not be those who cannot read and write, but those who cannot learn, unlearn, and relearn." Any guess as to when this person wrote this quote? Almost precedes me. This was in 1970. So this is actually very relevant if you're a computer scientist in this century, because this is a quote from a recruiter for a company with a 20% policy. A 20% policy means that this company is smart enough to say, for all of its employees, 1 day a week, you can spend that learning whatever you want. Because you've got to be learning all the time, and this is what they're looking for as a recruiter. This is a high-end tech company. As a recruiter, they're looking for people with a history and an attitude of learning. And so they recognize that the stuff you're learning right now has a shelf life. This person puts a shelf life at a decade. I would put it at maybe 5 years. So none of this stuff was stuff I learned as a student, not even close. And I would imagine 5 years from now, we'll be teaching something pretty different as well. So we're teaching the cloud because the majority of jobs in CS in the next decade will involve the cloud. In 2018, you saw this really massive shift of companies starting to move their infrastructure from on-site into the cloud. All of these sort of software and software services are being migrated to it, and we're building more and more things on top of it. And so the kinds of jobs, the skills, and the platforms that all of you are working with are completely changing. And so if you've seen this happening over time, you can see stuff like network administration jobs, which used to be six-figure jobs in the 80s and the 90s. You can see that being obsoleted by software-defined networking. You don't need to hire a network admin to bring up a virtual machine for you. Like all of you have been bringing up virtual machines. That used to be a job. It used to be my job to be able to bring up a machine with an IP address and a netmask and install an operating system. That used to be like a full-time job. Now it's a click. So you can see that happening. You can see virtualization software being obsoleted by infrastructure as a service. So VMware was making all sorts of money virtualizing servers, and now this is free. Like the virtualization software is now a commodity. The database administration jobs, these were multi-six-figure jobs. Like if you had your company jewels in a database, and something went wrong with that database, you called in a $300,000 a year person to try and save your database. But now, all of this stuff is being obsoleted by serverless databases, where you don't need that kind of expertise. You have these, and we'll get to this later on in this class, you have any sort of IT and operations jobs being obsoleted by these no-ops services, basically managed services, managed infrastructure. So now my knowledge of Unix and Linux and managing machines is completely obsolete. People don't need me to do any of that stuff. So I do teach it in the beginning part of this course because in the off chance that your first job requires you to do that level of management, you're going to need to know what's there. But yeah, you're going to see this move away from that, or away from those details. And then towards the bleeding edge, you can see there is an ecosystem of administrating cloud resources, all of these automation tools. So for example, locally, Puppet Labs, we have Terraform, we have all these, HashiCorp is the company. We have all these companies that are sitting there having proprietary, well, some of them are open, but like having their way of deploying cloud infrastructure, and some of that is being obsoleted by orchestration software that automates that stuff. So these are things that you have to be aware of, and if you see the thing shifting, you should learn the thing that's coming up next, is the message I want you to take home from this bit. Okay. So at the heart of everything that you see going on is the notion of abstraction and composition. And this is across disciplines. This is not a CS specific thing. So you see this in music. So keys, notes, measures, chords to form a symphony. You see this in math, language, physics, architecture, poetry, fashion design, and painting. Abstraction and composition. In fact, some of the best computer scientists that I've had, they started out in one of these areas and then are shifting over. Like we have a history in this department of former musicians going on and having these great careers in computer science. And part of that is just your way of thinking about abstraction and composition. How can I quickly acquire the new abstraction and then be able to compose those things with the other things that I know to build something of high value? So the goal of this course is really to focus on the abstractions, and then how do you compose them to build something better. And you'll see that this is a little bit different than what the other courses in this department offer. The other courses might focus on what is inside the widget that you're using. What is inside the abstraction? How do I, what are the details inside of the abstraction I'm building? So the Internet Protocols course, the Operating Systems course, the Database Backend course, and the Machine Learning courses, you're actually going in there and saying, hey, I wanted to build a better one of these. How do I do it? You also have courses that talk about how to make the widget architecturally. So functional programming styles, object-oriented programming styles, some of the ways we do the software engineering and testing. So this course really is just the abstractions that the widgets provide. And then we're going to compose them to build these more complex systems. Okay. And I want to give you a picture of how these abstractions have changed over time. I'm going to give you 3 sets of examples and show you how the abstraction level has shifted from really low-level stuff to high-level stuff, and we just take the low-level stuff for granted. We never even see the low-level stuff anymore. So we don't really teach it anymore either. Back in the 80s, we used to do networking by programming the packets themselves. So you remember those headers and TCP IP? We used to have to fill those fields in ourselves. What are those things and how do I program a packet and send it over to the network? And so this eventually gave way to what's known as socket programming. Some of you in the networking class, you'll see socket programming. That's a really low-level interface for programming over the network. It basically provides you a byte stream. A point-to-point byte stream, and then you have to put structure on top of that byte stream to speak a application protocol. Now in the 2000s, we're programming via URLs on top of HTTP. We're not even programming HTTP, we're just using that. And we're communicating over basically JSON as a data format. So again, you've raised the level of the way you communicate from point to point. And so we would never, well, I would never teach you the first 2 parts, even though that was what I learned. We've had a change in the way we do software engineering. In the 80s, it was a single computer, a single program, and a single operating system. So yeah, we didn't even have a network to communicate over, or it was a primitive one. In the 1990s, when the web took off, we have simple client-server applications. We have a web client and a web server. But now, when you're looking at a full-on application, you're talking about collections of machines. You're talking about multiple networks, and you saw this in your CDN lab, right? You're using a ton of different pieces to build that CDN application that you deployed. So distributed clusters, we have cloud deployments. We now are moving to multi-cloud deployments, where you're not only just the resources on a single cloud provider, you're composing resources on multiple cloud providers. So that's becoming the norm. We've had a change in how we deploy systems. So in the 1990s, you used to, if you were a company and you wanted to build an application and deploy it over the network, you bought your own building, you built it out, you bought all the servers for it, you bought all the software that you needed to run on those servers, you bought all the fiber to hook up your building, you bought the capacity from the ISP, and then you hired a bunch of staff to manage all of it. And so this was my first job. I was the staff to manage all of this in the middle. And then you pay for everything. And you pay for it even though it wasn't being used. So we pre-purchased all of this stuff, and then hoping that we would build it, and then they would come, and then we'd be happy. But until they came, all of those resources are basically idle, and we had to pay for all of it. And turns out nobody came to use our service, so that didn't last very long. In the 2000s, we got a little smarter. We're like, hey, if every company is doing that, that's really an expensive cost for each one of these folks to be building a small data center on site. So we went to this shared data center model. We had folks like Level 3 and Navisite were some of these companies. They would buy a big building in an industrial area. They would network the heck out of it. They would build out rack spaces. In fact, this Pittock block is an example of this. They had a bunch of rack spaces. They had the network connections. They bought these gigantic routers and switches to network everything. And then they said, hey, anybody in Portland who wants to host a website, you just host it here. And that's what people did. In fact, Portland State for a long time hosted a lot of their web stuff down there. And then you co-locate it to get the economies of scale. Now only one provider can buy an enormous data center and then amortize that cost across all of the customers that it's going to resell that to. Okay, so you get economies of scale, and you get it at the network and the physical space level. You only have to build one physical space, and you can invest in one gigantic network and then allow everyone to benefit. But this model requires companies to still purchase the servers to load up the racks in those data centers. It still requires them to install the software. It still requires all of these companies to have their own IT and operations staff to manage that. And then you would, like, if you were at Portland State and you're managing the website down there and all of a sudden the thing goes down, well, then you have to drive down there or walk down there, get into your closet, reboot the system, and then your Portland State is paying that person to do that at all hours of the night. So now what we have gone to is cloud computing, where the computing resources are done as a service. And this is like electricity supplied by the utility. And this allows you to get the economies of scale that's not only the physical space and the networking, but it's also the machines. The machines can be shared and rented out. The networks themselves are already shared, and the management costs is now amortized. I can have a single person managing a lot of the infrastructure, and that amortizes across all the customers. So this is basically statistical multiplexing between both the companies and the company's users to reduce the cost of that infrastructure that's being provided. So this is basically the cloud model, and this is why theoretically it should save a lot of money. Now, practically, it's only going to save you money if you keep track of your billing account, which I know some of you are now keeping track of now after you've gotten bitten by a $50 charge in 2 days or so. In fact, I should have done the billing lecture a lot earlier. I'm going to talk about billing in this class. Okay, so some of the advantages of cloud computing. The first thing is you can go assetless. You don't have to purchase hardware, and there's no physical space to build out. You have the ability to pay only for what you use. You can scale up and down your resources based on the demand for your site. And this can be done at a per second granularity with minimal upfront investment. You don't have to actually pay into it to get this ability. You don't have to say, oh, it's not like a Netflix thing where it's a subscription up front and then you can consume. You don't have to consume anything, and you don't have to pay you don't have to pay anything to be able to consume immediately. You can have a lot less IT and operations staff comparatively. So you don't have to have someone go down there and kick the machine. You're going to kick it programmatically through software rather than via a person. So you can automate and simplify a lot of the IT operations that used to be done manually. The big key is that you can have exponential growth in the machines that you deploy without an exponential growth in headcount. And that's really where you can scale the thing up, scale your services and your business up. The other thing you can do is get access to a bunch of value-added services that are provided in the cloud. So later on in this class, we're going to use the machine learning APIs that Google has. Like, you don't have access to those unless you are plugged into the cloud and have an account. Geographic Information System API, so Google Maps. So if you're doing your bubble tea thing and you want to actually put out a nice map of your bubble tea shop, well, then you have access to those APIs. And then you have access to these really large-scale data warehousing services. So if you want to keep track of all your log files of your site, you can use a back-end service that will store everything that your site generates seamlessly. Okay, so all of this is really raising the abstraction in systems deployment and development for us. Okay, so how did this come about? Well, the enabling technology, this is a confluence of a whole bunch of things. A whole bunch of things had to happen for this thing to take off. You have full-featured web browsers that can run applications within them. You have a huge drop in the cost of servers and a huge increase in their speed. You have the networking that was built out. You have this technology in large-scale distributed storage and file systems, so you can store things at a massive scale, yet still support querying that's really fast. So there's some algorithmic technology behind that. You have this, the maturation of virtualization software, hardware, and networks. So we talked about this earlier with the different virtual machine software and then software-defined networks for the virtualized networks, which you would need. And then you have a lot of open standards and software that is supporting all of this. So the TCP/IP protocols, the OpenFlow network interface, the standard network interface for programmable routers, Linux, Docker, Nginx, Apache 2, Python, all of these open standards that you're now able to build on top of. Okay, so you're on the cloud and you want to build up your application. So there's two scaling approaches that you would typically employ. And one is referred to as vertical and the other is horizontal. The vertical scaling is also called scaling up. So this is terminology that AWS in particular uses. They call it scaling up. And this is, the way you scale up is very simple. You just buy bigger iron. You upgrade your machine type. And so Google does this as well. So this is taking your single system and then going bigger with it. So you have a 1 vCPU system, and you can go all the way up to 96 with a large amount of memory. And you can explore the machine types on Google Cloud to see the vast selection of big iron that they support. And the idea is, hey, you know, maybe I have a database and I don't have enough users initially, so I put this on a small CPU. But then eventually, as I get more users, say I need something that does 10,000 requests, I'll just select a larger virtual machine. The issue here is that if I need 20,000 requests per second and I've already maxed out the machine that I'm on, I'm in trouble. And so this works up to a point, but then eventually you're going to need to do what's known as horizontal scaling or scaling out. And this is what most of the cloud infrastructure services are doing, especially the managed services. They're doing this scaling out operation. So the idea here is to replicate and load balance, and this is seen in the CDN lab that you did, where you were building the replicas. And then you would automatically add more servers, and these servers have to be identical, right? So that they can all process the same requests in the same way. And then you have some load balancer sitting in front that distributes amongst the replicas based on a policy. It could be round robin, it could be based on server load, least connection. So this is a picture from your lab. So this is a horizontal scaling option where you just replicate the machine type. And then over here you see that this is the template, and I have auto scaling on, and I'm going to do this based on the HTTP load. So this is done by the number of connections, HTTP load balancing, and then you go from 1 to 10. So this is horizontal scaling. And in the back end, for a lot of these services, they're doing this seamlessly. They're trying to hide this from you. Here we've done it explicitly, but we'll get to services that do a horizontal scaling seamlessly. Okay. The other thing to talk about are the kinds of migration models that you'll see out there if you're in industry. The three kinds of deployments are private clouds, public clouds, and hybrid clouds. So private clouds, if you have really sensitive data and you don't want to push, or sensitive operations and data, and you don't want to put any of that stuff off-site, then what you would do is you would ask Google or AWS to on-site their tools, and then for you to host the hardware, and then they just provide the software for you to manage those things. So this is what's considered a private cloud. And I think Microsoft just got awarded the government's cloud contract. I believe that's what they're doing. They're going to bring the Microsoft tools inside the government so that, because the government's not going to use public data centers for their stuff. So I believe that's probably going to be the largest private cloud distribution that we'll have on record is the Microsoft one that was like, what, they get $10 billion? So yeah, maybe they'll be hiring in Washington, D.C. if you want to move. I'm not going to move. But public clouds is basically what we've been doing. We're like, hey, we got a data center. It's in the Dalles. Everyone else is using it. But that's okay. I can share. So it's hosted, operated, and managed by Google. And then the security and the day-to-day management of the infrastructure, the hardware, is done by the provider, by Google. And then you don't have to pay that engineer to swap a disk out. Take out a pizza box, which is like a server, and replace it because the CPU died. You don't have to pay that person because Google has hired that person. In fact, it's probably a robot by now, but they're taking care of that. You also have a ton of hybrid cloud deployments. And so for these, you have sensitive parts of an enterprise that have to stay on site, but the vast majority of the rest of it could be done in a public cloud. And so this is where you had that virtual private cloud where parts of it were kept on site, and then you virtualize the network in between the public and the private to get a hybrid deployment. So that's what they mean by hybrid clouds. And there's many reasons to do hybrid clouds. Regulatory issues, so OHSU needs to have their patient data on site because it's a federal regulation. So they can't be pushing patient data out to the Dalles, or no, they were looking at AWS, so it'd be out to Umatilla. And so they would have to put they'd keep their stuff on site, and then they would borrow some services from the cloud, and these sorts of things. Okay. So to give you some motivation for the power that the cloud gives you, we're going to talk about Snapchat, which, I don't know, people still use Snapchat here? Yeah, they sort of gotten eaten by Facebook stories and Instagram stories. But this was a small startup in 2011, no data center, no operations team. It was just 2 developers with a very simple app. And it was so simple that when Facebook wanted to acquire them and they refused, they went and they built this app called Poke, and they built it in 12 days. It was basically a Snapchat knockoff. And they were like, this is how quickly you can develop and deploy a service like Snapchat, right? And so how did they do this? Well, eventually this service, so in 2 years, it grew to tens of millions of users, and it was handling hundreds of millions of messages at that time. And it started out with just 2 software developers. By 2017, it's at 170 million daily users, 3 billion photos and videos per day, and this is the growth curve. So how did Snapchat how are they able to handle with all of this growth with just a couple developers? Well, a couple years ago, they announced this. They were paying Google $2 billion for their services. And if you look, it was basically operating on this thing called App Engine. An App Engine is something that I'm going to have you do your lab. Your homework number 4 is an App Engine app. And the idea of App Engine is just give me your app and I'll scale it to however many users you want it to scale to. And that's the power of a cloud computing model. Okay. And so this allows any startup company to focus on their core competency. And if this means if you really hated the first half of this course, then the cloud is for you. The second half of the course is where you're at, right? Like, give me my Python and JavaScript. I don't care about Linux and Nginx and that kind of stuff. Like, that stuff, that was traumatic. I'm gonna forget about that. That's compartmentalized away from my mind space. And this allowed, like, using App Engine, they could just focus on the app, just the code to implement the app. And it allows you to, the actual service itself allows you to deploy new versions very quickly. And it also allows you to leverage the scalability of the Google infrastructure without you having to engineer it. You don't have to engineer the scalability into your app. If you're using the APIs properly, it does it. Okay. And the idea is that at all levels in App Engine, you're able to horizontally scale the application code out. So that's where the power is. And we'll get to this next class. Okay, so that is the motivation for the cloud. I'm going to give a brief, you've already used Google Cloud quite a bit, but I'm going to run through some ins and outs. Now that you're going to be full on doing Google Cloud Labs, I'm going to give you just a brief intro. The reason why most of the labs are on Google Cloud is that I felt at the time this was way more student friendly than AWS was. You can get these credits without credit cards. You can get a full Google Cloud account. So you've noticed with Vocarium, you've got this restricted AWS account that only can provide resources in Northern Virginia. So this is a full-on. You have a full-on Google Cloud Platform account with what you have. And you can use your pdx.edu account for the credits. That's all. We're a G Suite school, so it made sense for that. And it supports all the open source APIs, so if you're really worried about learning Google Cloud and not being able to shift over, well, the nice thing about Google Cloud is that they are natively trying to support the open mechanisms for managing things. So Go and Kubernetes, they put their big arms around Docker and containers. So a lot of the stuff that you're going to run in these labs, you can shift over and easily run it on AWS. Most of them, I should say, not all of them. And so you'll find that the abstractions that you're going to use on Google Cloud, there are similar abstractions on AWS. It's just the marketing's different. It's a lot less straightforward, the marketing on AWS, as you'll hopefully run into, or not hopefully, you'll run into, definitely. They also have a generous free tier. So there are people who have gone through this entire class in under $1. I think it was under $1. No, that was the web security. It was like under $5 is the record. Do every piece of this lab in under $5, or every lab in this course for under $5. And the reason why is that there is this pretty generous free tier. And so when you deploy your final project, for example, and it's going to, if it's on App Engine, you get 28 instance hours per day before it starts charging you money. And so what I would recommend is when you deploy your final app, you just leave it there. And then if you have it on your resume and people want to see what your project is, they'll click on it. It'll bring up your app on demand, and then they can see what you have at very little cost to you. So that's what I would recommend. Cloud Data Store has a generous sort of limit on the free tier. The Vision API, you can do 1,000 queries a month. BigQuery has the first terabyte of processed data is free. So all these things make it easy to use Google Cloud. So in Google Cloud, you've seen that the organization of Google Cloud is done around projects. There are a lot of companies with multiple projects for each of their sites. And the reason why you would create different projects for different kinds of sites is that every site will need its own security policies. They have their different dev teams. They have different ways of managing their teams. And so you would typically build those as separate projects in your organization. They'll have separate billing. So if you want to break out the costs per site or per group, then you would separate out the billing. And you would have, this is for security purposes, you would have a set of enabled services that are restricted just for the app that you're hosting inside of that project. And this keeps someone from hijacking a resource in your project and using it to do all sorts of other things within that project. So you do have some isolation for security purposes. So Google has more than 100,000 projects that it uses to run all of its properties. It's just an interesting statistic. So for Google Cloud, and this is the same terminology that AWS uses, they have things called regions and zones. So regions are geographic areas where the infrastructure is, and then you see that these are coarse. So US West is a region, US East, US Central, and in fact, Google copied a lot of the naming convention from AWS. They just wholesale copied that, and you'll see for the IAM security stuff, they just copied that stuff wholesale, a lot of the terminology from AWS. So the regions and the zones are similar to AWS. Every region has a collection of zones, and these zones are isolated locations within that region. And so this is the US West 1 region, which is Oregon. And then within Oregon, there's different zones that are separated. So West 1A, B, and C in this case. And then when you're navigating your cloud resources, you'll see that there are 3 ways to access any of your resources in the cloud. The first is the Cloud Console, which is the web UI. You go to console.cloud.google.com, and you got this nice GUI in front of you to start VMs, to tear them down. You also have the Cloud Shell interface. So when you click on Cloud Shell, you can say gcloud compute instances create, and you can create a VM or delete a VM from there. And then you also have this REST-based API, and it's basically an endpoint that if you submit a create or destroy operation to that URL, it'll create and destroy a virtual machine, as you would suspect a REST endpoint would do. It turns out all of this stuff is basically doing the exact same thing. These are interfaces that basically do JSON over HTTP that hits the REST API. Almost everything in the back end is just a REST API. There's also a 4th way, this programmatic access. So you can pip install the Google Cloud SDK inside your Python application, and you can have a Python way of creating infrastructure. And you'll see if when you get to there's this Thundercloud CTF exercise that you'll be doing, there is this deployment manager script that's written in Python that sits and deploys all of the infrastructure for the particular level that you're doing. It's just using the Google APIs, the SDKs built into Python to launch all those resources. Okay, so in terms of command line GCP, typically there's multiple ways of getting command line GCP onto your computer. So I had Cat install these one quarter. You can basically install the Google Cloud SDK on your Ubuntu system. So if you actually want the gcloud commands on your laptop rather than using Cloud Shell, then you would just install Google Cloud SDK, and then you would have native access to gcloud gsutil, which is the command for interfacing with storage buckets, and then BQ for BigQuery. The other thing you can do is you can do a Docker pull on Google/Cloud SDK, and then you do a Docker exec, and you Docker exec a shell onto that container, and then you have the full-on, up-to-date Google gcloud SDK in a Docker container. So if you're in a pinch and you don't want to, or if you really dislike the Cloud Shell, I've had no reason to do anything other than Cloud Shell, but maybe if you're like elite users and you actually want something different, you could do one of these 2 things to get your gcloud command locally. Okay, so typically you're going to access this. I would recommend accessing this through Cloud Shell. So this gives you containerized. This is a containerized version. It's basically this. What Cloud Shell is, it's this done where it's mounting a home directory that has your files in it. And apparently, so Leslie was really bummed. She hadn't launched Cloud Shell in like several months, and they deleted her home directory. So, yeah, this is why you want to do a git push. Like if you're doing something in Cloud Shell that you want to save, I would do a git commit. And it took many months for them to delete it. Usually it keeps it around. But basically, what this does, the Cloud Shell is basically to do a Docker run on Google Cloud SDK. And it's going to run a containerized version of Linux, and then it's going to mount a directory, and it's your home directory that's associated with your address. And then within this container, it's got all of these packages that most of us want. So it's got NanoVim, Python 3, virtualenv, etc. Okay, but if you have this container and you do an apt install, that doesn't get saved because you're not doing a Docker commit on that container image. And when you exit out a Cloud Shell, it gets rid of your container. It does a Docker RM on that container. So this is why I don't know if it's happened in this class, they're like, hey, I did an apt install of this, that, and the other, and the next time I launch Cloud Shell, it wasn't there. And the reason why is because it's doing this Docker container, and when you instantiate the vanilla Docker container, it doesn't have any of the stuff that you installed previously. You don't commit to the container image, it basically launches it. So I wanted to mention that just in case you're wondering. And that's how this Cloud Shell thing is implemented there. Okay. So that is an intro. The next thing I'm going to do is cover IAM.